All right, let's talk about one of the most important ideas in the history of AI. We're diving into a neural network called ResNet. In this thing, it didn't just nudge AI forward, it completely changed the game, all thanks to an idea that is, believe it or not, surprisingly simple. But to really get why ResNet is so brilliant, we have to start with a puzzle. A really frustrating one for AI researchers back in the day. What if you tried to make your AI model more powerful? You gave it more layers, more capacity to learn, and it actually got dumber. This wasn't just some small hiccup. This was the big problem, a central paradox that was holding the entire field of deep learning back, a puzzle that somebody had to solve. See, at the time, the common wisdom was pretty straightforward. If you wanted a more powerful AI for something like image recognition, you just add more layers. Deeper networks have more moving parts, right? So they should be able to learn more complicated patterns and get more accurate. It just makes sense. Well, yeah, it turned out to be completely wrong. The data, the actual results, told a very different story. What you're looking at here are the error rates for training and testing. Now, in both charts, that red line, that's our supposedly smarter, deeper 56-layer network. And look, it actually has a higher error rate than the shallower 20-layer network in yellow. The bigger model was failing. This baffling problem got a name: the degradation problem. And it wasn't just a minor annoyance, it was a massive bottleneck. It plagued famous models like VGG and basically put a hard stop on how deep, and therefore how powerful, our AI could get. But you know how it goes. Every frustrating problem is just an invitation for a brilliant solution to show up. And in 2015, a new hero emerged to break right through this wall. A team of researchers, Kaiming He, Shangyu Zhang, Xiaoqing Ren, and Jin Sun, published a paper that would literally change everything. They introduced this incredibly elegant new architecture called the residual network, or as we all call it now, ResNet. So, what was their revolutionary idea? How did they crack this impossible code? The answer lies in something so simple, it's almost funny: the genius of taking a shortcut. Okay, look at this. This is the heart of ResNet. It's called a residual block. You see the normal path where information flows through the layers, but then you see that curved line going around them. That's a shortcut connection, sometimes called a skip connection. And that little line, that is the key to this whole thing. To really get why this is such a game changer, think about it like this. Before ResNet, each block of layers had this incredibly hard job of learning a whole complex function from scratch. But with ResNet, the layers are asked to do something way easier. Just learn the small change, or the residual, from what you already have. So instead of forcing the network to figure out the final complicated output all on its own, that shortcut just passes the original input forward. Now all the layers have to learn is the difference, or the adjustment that's needed. And it turns out it is so much easier for a network to learn a small tweak than it is to learn a whole new transformation from the ground up. So how do they work exactly? Well, these skip connections create an alternate path. They literally bypass a few layers so the original info can flow straight through untouched. And here's the most brilliant part. If a particular layer is actually making things worse, the network can just learn to ignore it. It can rely on the shortcut, making the adjustment basically zero, and just pass the original input through. It's like a built-in safety valve. And get this, the elegance of this little shortcut didn't stop at solving the degradation problem. It also fixed another huge, infamous issue that had been plaguing deep networks for years: the vanishing gradient problem. You know the game of telephone, right? Where a message gets whispered down a line and gets all distorted by the end? That's kind of what happens here. As the learning signal, the gradient, travels backwards through a super deep network, it can shrink and shrink until it's basically zero. When that happens, the early layers of the network just stop learning. They're not getting the message. But ResNet's shortcut connections, they're like an express lane, a superhighway for that gradient. They give the learning signal a clean, direct path to flow all the way back to the start. This keeps the signal strong and makes sure the entire network, no matter how ridiculously deep it is, can keep on learning. So, how do you build a full network with this? Well, it's actually beautifully modular. It's like building with Legos. After some basic first-step processing, you just stack these brilliant residual blocks, one after another, to form the deep core of the network. Then, at the very end, you toss in a couple of layers to wrap it all up and make the final prediction. By stacking these simple blocks, you can build incredibly deep and powerful networks. So, solving two massive problems with one simple idea, that's already legendary. But ResNet's true impact, its lasting legacy, is how it completely redrew the map for the entire field of AI. I mean, before ResNet, a network with a few dozen layers was considered deep. After ResNet, we're talking about networks with hundreds, even over 1,000 layers becoming possible. It became the go-to, the standard blueprint for almost every computer vision task: classification, object detection, you name it. Its principles have even been borrowed for totally different fields. And, so importantly, it became the backbone of something called transfer learning. And why should you care about that? Because transfer learning means you don't need a supercomputer and a million cat pictures to build a great AI. You can take a ResNet that someone else has already trained on a massive data set and use all that pre-baked knowledge as a powerful head start for your own project. It really democratized access to high-performance AI. So in the end, ResNet taught us this really profound lesson. In a field that's obsessed with making things deeper and more complex, it proved that sometimes the most elegant, most powerful way forward is to build in a simple shortcut. It really makes you wonder, what other huge problems in AI or anywhere else are just waiting for us to find the right way to skip ahead?